It is a real pleasure to be here this week, to see many old colleagues again, and also because this week was a major week for the JADES project with our data release. And so to be here at Cambridge with so many other JADES collaborators has been really very special. So I'm going to be talking today about looking into the early universe with JWST. I'm going to try to start off with some broader comments, and then we'll get more specific into JWST and then into the JADES survey. So of course the topic here is galaxy evolution, and at low redshift we see these beautiful pictures of galaxies and are also confronted with how complicated galaxies can be. And one of the major things we try to do is understanding all this complexity and testing it by going out to the early universe, because the first generations of galaxies probably started at a redshift of 10 or 20. And galaxy formation we understand is a very nonlinear process as gravity is trying to pull material together down to form stars and black holes. All those objects are able to produce gigantic amounts of energetic feedback and push the material back out. And so galaxy formation really ends up as a self-regulated process, and we're trying to understand the mechanisms of that self-regulation. And one way to try to understand that is to go to conditions that are more extreme or somehow different. And a big field of that is to work then at higher redshifts. And so I will be focusing entirely here on looking at galaxies at high redshift. And of course, the key technological aspect of this is that at high redshift, all the light that was emitted in the optical and ultraviolet by all those hot stars has been shifted relentlessly off into the infrared. And so we are driven to need a large infrared telescope to actually work on it. And of course, this was the motivation over 25 years ago for the James Webb Space Telescope, shown here with, I think, a very small fraction of the people who've spent 2 decades bringing it to life. So JWST is, the next big flagship mission out of NASA. It's the largest astronomy mission since HST. It's been a really long time coming. So as I say, it really got started in the 1990s. I joined the project in my first year as a faculty member at the University of Arizona when Marcia Ricci walked in and asked if I'd like to join onto her project as a sort of house theorist. And so now we're 22 years later with this thing actually up in space. So, sometimes when a project gets very delayed, you worry that it's being lapped by other projects that were more fortunate. But in this case, I think that JWST, the opportunities of being in space with a large infrared telescope are so overwhelming that the telescope's going to have just an astonishing impact across most fields of astrophysics. So the telescope is optimized for 1 to 5 microns, extending out to 28 microns. And so I think just something to reflect on is why. And of course, one reason is the reason I'll be focusing on here, that cosmological redshift is just shifting all of the ultraviolet and optical light out into the out into the infrared. But of course, there's other major drivers for the infrared. When we look at dusty objects, the dust is very good at absorbing or scattering bluer light. And so only in the infrared can we actually look through the dust to see the underlying objects. A next major reason is some objects are just pretty cold. Exoplanets and cold stars are better studied in the infrared. There are, of course, unique diagnostics. The rho vibrational transitions of molecules, the pH features in the interstellar medium, even molecular hydrogen. These things are actually best seen in the infrared. So I apologize that I'm going to focus in this talk entirely on what many people would call the near infrared, leaving aside the really important regimes that go off beyond 50 to 100 microns with the far infrared. But I'm going to focus here where JWST is. I thought I'd include this slide just to remind you why working in space is such an opportunity at these wavelengths. And it's because infrared is, from the ground, is much harder because the telescope is glowing and the atmosphere is glowing. And so the backgrounds, even at 1 to 2 microns, are 1,000 times fainter in space than they are on the ground. And when you go out beyond 2.5 microns, even when the atmosphere isn't completely absorbing the light, you're really facing shortfalls of factors of 1 million or more. So it's enormously darker in space if you can cool your telescope. And when you think about what is your limiting background in space, it's largely coming from the zodiacal light in the solar system, and that is a combination of the backscattered sunlight, which peaks in the blue because the sky is blue, and so scattering things like to scatter in the blue. And then that dust also, so that's reflected sunlight, but the dust also is absorbing the sunlight and heating up to room temperatures and re-emitting with a peak out at 10 to 20 microns. And so there is a dark window between 2 to 5 microns where that there's a minimum in the background from in space. And that is fortunate because that's exactly where all of this high redshift light has shifted into from the optical and ultraviolet. And so it's just a great place to work if you can actually build a large cold space telescope. So JWST is really a technological marvel. It is immensely complicated because it's big and it's cold. So you have to be able to fold the whole thing up into the rocket. You have to make it really light, which meant that it uses crazy materials to make it really light. And then all these cryogenic optics have to be in perfect alignment, but they have to simultaneously do that where they have to be held tightly enough to survive launch. You can't have the instrument jiggling apart into pieces as you launch it, but not so tightly that when it cools down, the differential coefficients of thermal expansion don't crush the optics on the way. So it's just enormously complicated to get all this to work. And of course, since failure is not acceptable, you spend more and more and more money to try to assure that you won't fail, and then you get more scared that you might fail. So, okay, so I think as you all know, astronomers got a fantastic Christmas present just a year and a half ago with a successful launch. In fact, a launch that was so successful that the simple perfection of the launch itself may have doubled the life of the mission because the rocket saved the orbit insertion was so accurate that the telescope was able to save a lot of fuel, of its own fuel, and so it actually has more station-keeping fuel than was projected. So this is just extremely important for all the young people in the audience because as a 5-year mission, you worry that you're going to work and have a good 5-year run, and then it's not clear what you're going to do in your postdoc. And with a 10-year mission, you think you're going to have a good postdoc, and then you're not sure what you're going to do as a faculty member. But with a 20-year lifetime, you actually begin to talk about having a substantial academic career and being able to bridge to the next large program. So it actually is it's a tremendously, well, knock on wood that the thing lasts this long because of all the other things that can go wrong, but it is a really great thing that the lifetime is looking good. So of course, this mission was over 20 years in development with all possible forms of sociological torture, but after all that, it all works. There's really no major lean in the system that I'm aware of. So just, fantastic thanks to all of the engineers and everybody who actually helped to actually get this thing into orbit and all commissioned. So it would be a shame to not show you some pictures. The next few slides will just be some fun pictures. But of course, this is what we had before from Spitzer, which was a fantastic telescope by its own stead. But then this is the same region in James Webb. Just the angular resolution of a 6.5 meter telescope versus an 85 centimeter telescope is undeniable. Here's the picture from the first released image of this beautiful cluster. I'll have a lot more to say about all the little dots in the picture, but here's another beautiful cluster picture. There's just galaxies everywhere when you look at these things. The nearby galaxies make particularly beautiful pictures. Here's the Cartwheel galaxy glowing in the mid-infrared wavelengths. Here's another NGC galaxy. The level of detail that you get and the level of opportunity that you have because of all the different filters and wave bands and different combinations is really just much more effective than what you normally get with a space telescope where you have a handful of fixed filters. You just see this over time and time again. So again, another beautiful picture, a reminder that galaxies can be messy. Okay, so as someone who has spent most of the last 20 years working on ground-based surveys like SDSS or DESI and dealing with the ground-based images that come from that, I have to say that the depth is actually kind of disorienting. So this is a picture from the Dark Energy Survey. This is a perfectly reasonable telescope doing perfectly reasonable imaging. They've got this over, a fair chunk of the sky, but that's about 15 minutes per band on a good 4-meter telescope. So that's what you get there. And then that's what you have in JWST. That object there is that one there. Those are at redshift 0.6. These couple down here at redshift 2.5, you can't really even see. Even these ones up here at 1.2, you can't really even see. So, I mean, you look at these pictures, you put them side by side, and I can't even figure out how to match up the images often. I've gone to try this. It's really hard. Of course, the reason part of this is happening is that galaxies are extremely bright in the infrared. So here is a dramatic example from HST. You see this nice galaxy here. You don't see much down there. That's 850 microns. And here it is in JWST, peaking up in the infrared. This is a grand design spiral at redshift 2 that you just couldn't really see in the optical, despite the fact that it's forming stars, right? So you sometimes think that all these star-forming things are going to be really bright in the UV, but not always. It's a tremendous improvement. So this is the deepest image ever taken with Hubble Space Telescope in the ultra-deep field in the H-band. And here's the same image in JWST. That's 6 days, that's 9 hours. And we have dozens of times more field of view than that already imaged. So, it's amazingly better. I focused on the imaging, but the spectroscopic revolution is, if anything, I think, more impressive. We've just never had access to spectroscopy beyond 2.5 microns that was ever deep enough to get to faint galaxies at high redshift. Like, we've had some spectrographs at, Spitzer had a spectrograph from 5.5 to 25 microns, but you just can't get deep enough with those telescopes. So this is really the first time we've ever been able to study rest frame optical properties of galaxies at high redshift. And near spec is so amazing that you don't just do this one object at a time, you can do multiplex of 150. So you can really get just amazing spectra at high redshift. Okay, so I work on the JADES survey, which is a joint venture between the NIRCam instrument team and the NIRSpec instrument team. And we contributed together about 770 hours of guaranteed time. This is about 1 month of the telescope towards doing deep imaging and spectroscopy in 2 famous fields, the Goods North and Goods South field, which you would also know as the Hubble Ultra Deep Field and the Hubble Deep Field. So these are the 2, I think, premier deep fields on the sky. There's been a couple decades of investment, well, really at this point 25 years of investment, from all major facilities into these fields. And so this is the attempt within James Webb to really bring the full power of James Webb to bear on these fields. So, some montage of pretty pictures from the survey. Each of these pictures is of order 5 to 10 arc seconds across. So these are tiny little pinpricks, and I'm not going to go through all of them, but you spend, you just go out and look at the images and you're constantly amazed at what the universe can actually do. Okay, so now I want to turn attention towards really trying to focus towards higher redshift galaxies. And as I start this, I want to remind you that how we go about detecting high redshift galaxies. And a key way that we try to do this is with the Lyman alpha dropout, so Lyman dropout galaxies. And that's because there's enough neutral hydrogen in the intergalactic medium that when a photon of 1216 angstroms tries to propagate through the intergalactic medium, it doesn't get very far before it meets a neutral hydrogen atom, excites the atom from the ground state up to the first excited state, and then a nanosecond later decays back, emitting the photon, but in a different direction that's no longer coming towards the telescope. So light at 1216 angstroms is extremely well scattered out of the beam. And any light that was emitted from the object shortward of 1216 angstroms is at some point in the journey going to come into resonance at 1216 angstroms as it redshifts along. And so you get this complete dropout shortward of the rest frame 1216 angstrom. So one of the really good ways to detect high redshift galaxies, at least in this wave band, is by looking for this characteristic drop in the spectrum. So, of course, this has been going on for almost 30 years with the progression of bands starting with U-band dropouts and then on further. But here we are in JWST, so these are the, here are the bands. So this is 0.9 microns, 1.2, 1.5, 2.0, 2.8, 3.4, 3.6, 4.1, 4.4. And you see this particular object is well detected until it isn't in the last band, or the shortest band. So this object's about redshift 9. The next one down is observed in all bands until it isn't in the last 2. So it's dark at 1.2 microns. That's about redshift 12. This next one is dark in all bands until it isn't seen in 1.5 microns. That's probably redshift 14. So that's the idea that we're looking for. Here's some other examples trying to dress this up a little more. So here's, again, all the filters, including some HST filters. And here's the picture of the SED dropping out hard. This example is at redshift 8. That's about 28th magnitude. Here's an example at redshift 12. Again, this one drops out sort of around 1.4 microns. Here's another example at redshift 13. Again, a complete dropout in the 1.5 micron band. I think this thing is dropping. The battery is also dropping out. So just beautiful detections, and then kaboom, nothing. And that's at 29th magnitude. So we're able to find these things once we finally go faint enough in the infrared. Of course, the question is, are these really at high redshift? Where they're consistent with being at high redshift, but are they really at high redshift? And at least in some cases, the answer is yes. So we were able to take JWST spectroscopy. Emma Curtis Lake led the spectrograph paper here. So here's the spectrum of the galaxy with JWST. This one's at redshift 10 with the drop. Here's redshift 11 with the drop. Here's redshift 12 with the drop. Redshift 13 with the drop. So, I mean, these were extremely gratifying data to get. And, it's worth remarking that this is continuum spectroscopy at 29th magnitude, which is completely crazy that would ever be possible, but here we are. We were able to characterize these galaxies. They're small, but it turns out that 2 of them are actually spatially resolved at about 0.02 to 0.04 arc seconds. So that they're not all just complete point sources. The stellar masses are 10 to the 8 to 10 to the 9 solar masses. So you can start to characterize from the colors. So this is where we were in December with this first release of spectroscopy. Just very gratifying to actually be able to confirm that some of these high redshift candidates were indeed at high redshift. But of course, we want to go on beyond these examples. So Kevin Hainline made these slides showing that before JWST in these fields where we're looking goods north and goods south, there were a few dozen candidates and a few candidates at redshifts greater than 10. This is redshift 8, 10, 12 versus magnitude. So that was where we sat before JWST. After our initial spectroscopy and the analysis of a little bit of other shallower data, we added a few more. And then on Monday and Tuesday, we were able to release our full catalog from the sample, and so now we have this. So this is over 700 galaxies observed in goods north and goods south, and 93% of these are new. So, there's just an enormous population of high redshift candidates out there. These are all still candidates. We are trying to, we'll be trying to confirm them. So far, we have spectroscopic redshifts of 42 of them by hook or by crook and various heterogeneous methods. But so far, all 42 of them are at high redshift. So at least for the ones we've been able to do so far, which I suspect are the easier ones of them, we have a good batting average. I'm sure this will get harder as we get out to higher redshifts. I'll have more to say about that at the end. More generally, photometric redshifts in this field, there's so much data with so many different bands. We have over 20 bands of space-based imaging for a bunch of these, subarc second space-based imaging for a lot of these objects. And there's so much spectroscopy in these fields, from the VLT from JWST and others. So you can actually do really good photometric redshift calibration, even with calibrators that are themselves at 26 to 28th magnitude. So I think that's going to be a real legacy of these deep fields. Okay, so a lot of these galaxies have complicated shapes. So again, they're not all point sources. In fact, a lot of them are multi-component. And so this is going to be really exciting. We're going to be able to study things about the morphological buildup of galaxies at these high redshifts. They're spread across the fields. So this is the good south field. I think I'm going to switch to the stick here. The good south field, the goods north field. So we're also going to be looking at clustering in these fields. And we do see some hints of early clustering. So this is data that Jake Helton and Fengwu Sun worked on, where they took the slitless spectroscopy data that came from the Fresco survey and searched for spectroscopic lines around the location of JADES high redshift candidates. And this was the set they found in this redshift range between 5.2 and 5.4, and there was a big spike in the redshift histogram. And then when you plot where those objects are, they're all in this region. So there is structure starting to appear of galaxy groups or protoclusters, whatever you want to call them, at high redshift. And we see other examples of this, of these sorts of things in the field. So, although we're at high redshift and the overall matter field is not very evolved, but the clustering bias of these galaxies is so extreme that you still can see clustering. Turning to spectroscopy, just beautiful spectra that are coming out from the team. These are examples of high redshift galaxies from redshift 5 to redshift 9, where you can see, the oxygen-3 doublet, H beta, H alpha, so forth. I mean, there's a lot of information in these spectra. So for example, Alex Cameron led the group in a paper looking at line ratios of these. And so this is the oxygen-3 to oxygen-2 ratio versus the sum of the oxygen lines compared to H beta. This is one of the classic low redshift diagnostic plots. And these are where low redshift galaxies sit, or the bulk of them sit. And here's where these galaxies are sitting. So they are consistent with these lower metallicity, more extreme ionization states. And one thing that's sort of very clear in the spectra is that oxygen-3 is always much stronger than oxygen-2. I mean, or maybe always is a little bit strong, but it's characteristically much stronger than oxygen-2. So you get these enormously strong oxygen-3 lines and H alpha lines walking through the spectra, which is very useful. But they're not all rapidly forming stars, and so Tobias Lusser, who's a student here, found this beautiful example of a galaxy at redshift 7.3 that doesn't show emission lines. So this is sort of an example of a post-starburst galaxy at extreme redshifts. Still has enough UV emission that you can see the Lyman drop. But I mean, this is, I think, indicating not all the galaxies are playing by the same songbook. They're doing different things at different times, and I think that's going to be very interesting. One bet that we made in JADES that I think is really paying off is that we included a couple of medium band filters at 3.3 and 4.1 microns. And it's turned out to be extremely helpful because these strong H alpha and oxygen-3 lines, as they walk through the spectra between 3 and 5 microns out at redshifts of 4 to 9, are just walking through these filters. And we're able to get much better photometric redshifts because of this. And we're also able to detect these strong lines. So here's an example from Natalia Villanueva, who's going to be joining here as a one-year student, master's student in September, where the image on the right is the line emission from 3.6 microns, and the image on the left is the ultraviolet 1.1 micron image. So this is star formation indicated by H alpha. This is star formation indicated by the UV. And you can see that there's some interesting morphological variations between the two. Another example of these morphological differences comes from William Baker's paper, a student here working with Sandra, where they were able to study the detailed multi-band morphology of a redshift 7 galaxy and found that there was clear evidence for a star-forming disk, that the emission lines were preferentially along the outside of the galaxy, and the core of the galaxy was forming stars much more weakly. So this is, an indication of an actual bulge and disk starting to grow at redshift 7. So I think that my takeaway from these results and others is that galaxies at redshift greater than 6 are really complex and diverse. It's not that these things are all doing one particular story. We see variations in star formation histories. We see variations in bursts and emission lines. We see examples of quiescence or lulling. And we're starting to see some correlation of these things with environment. So there's a whole story that these galaxies are acting out at high redshift, and it's not just, everybody sits on the star forming main sequence and does exactly, has exactly one specific star formation rate. They're dancing around as they go around. Okay, turning to the next item. So, as I said, we were extremely excited in December to publish the first 4 galaxies at spectra at redshift greater than 10. But we were a little bit disappointed that we didn't see any narrow lines in the spectra. Emma will tell you, you can still get constraints out of upper limits, but she would have been more excited to get constraints out of detections. This is because the strongest lines in the spectra at redshift greater than 9.5 have shifted out beyond the 5-micron band of near spec. And so this changed instantly with GNZ11. This is the brightest galaxy in the field. It was known from HST, discovered by Bowens and Ush with HST data. And JADES was fortunate to be able to observe it both with imaging and spectroscopy. We published this in February. So these are the images, again, 4 microns down to 1.5 microns, and then nothing in 1.2 and 0.9 microns. So just a beautiful quintessential dropout, mildly resolved. And then this was the spectra, which just was everybody was gasping, where you just see about a dozen rest optical and rest UV lines coming from this galaxy. It's just fantastic. You see these things and you're going to be able to do interesting stuff with them. Really strong Lyman break, but also an indication of a damping tail from the Gunn-Peterson trough. I mean, the whole thing, just textbook. That was the prism spectrum. There's also high-resolution spectra, which this plot just does not do justice to, but Roberto and his team have been working really hard to figure out how to manipulate this. There's one really weird thing about it, is that's Lyman alpha. So what's Lyman alpha doing in emission at redshift 10.6? Because after all, the whole story of reionization is there's a neutral IgM back beyond redshift 7, and it's supposed to absorb all the Lyman alpha. And yet here we are with this galaxy that is showing very, very clear and strong Lyman alpha emission. So it's a little bit redshifted. But this is an indication that this thing must actually have been able to create a substantial ionized bubble around itself, even at redshift 10.6. So this is, reionization starting to reveal itself as a patchy process. This isn't the only example. We have another example that Ayush Saxena published that from the team that has another Lyman alpha line. This is at redshift 7.3, so lower. But it's whopping strong. 400 angstroms of rest equivalent width in Lyman alpha is extremely strong. So these things are out there. Gareth Jones released a paper this week showing that indeed we do confirm that Lyman alpha is becoming more rare at high redshift. So this was as you go from redshift 4 to 5 to 6, the fraction of galaxies that show strong Lyman alpha emission is increasing. Apparently the galaxies are getting lower metallicity or whatever you think the reason is, but that is increasing. And then as was known from previous work, it drops. And we do indeed find a drop as you go out towards redshift 7. So, overall, I think the story of the universe is becoming substantially more neutral at these redshifts, but apparently not uniformly so. One of the fun things about GNZ11 is we don't think that it's alone. We find 9 other candidates with consistent photometric redshifts within a couple arc minutes. So this object is very likely part of its own association out there. So what is it? probably an AGN. Roberto has and all have argued in a paper that the details of these lines, I'm not going to get into it, you should ask him to give a talk here too, is that the details of these lines argues, I think actually really quite convincingly, that the lines are being created in a region of very high number density of atoms, and that is more akin to a black hole accretion disk than star formation. And so if we take the line width seriously, we come up with a black hole mass of around 2 × 10⁶ solar masses. So it's a wimpy black hole, but it's at redshift 10.6. So this next item it was serendipitous, but in the first JADES spectrum of GNZ11, Roberto noticed a weird wisp of helium-II 1640. Like you just looked along the slit, and the helium-II line was more extended than it ought to be. Helium-II, of course, is the result of extremely high energy photons. You have to have a photon of 54 electron volts to pull the second electron off of helium and create this recombination cascade. And so we proposed to observe it again with the integral field unit, because this was at the end of the slit. It was this totally serendipitous thing. So where is this blob coming from? And sure enough, so that's GNZ11 over here. And or maybe it's that star, I guess. And then there was this blob in the helium-II line out here. And you do not see anything in the continuum image at that location. So this is not just a helium-II line, which is already a very energetic thing, but it is a helium-II line that has no measurable counterpart in the rest frame ultraviolet around 1500 angstroms. So that means that the spectrum that's doing the ionization has to be extremely, extremely hard. Because, right, you have a lot of 54 electron photons and very few 10 electron photons, 10 electron volt photons. So you have to have a very, very blue spectrum. Well, one possibility is that population 3 stars are expected to be very blue. So that's one hypothesis. This is a lot of energy. So the amount of energy you need to actually drive this much helium-II, which we are seeing again at redshift 10.6. So the amount of energy you need corresponds, if you then translate that through the Eddington argument, would correspond to a mass of about 10⁶ solar masses of stuff. So this is not like a single, X-ray binary or something doing something that we're seeing. This has to be a big population of stuff, or a direct collapse black hole, or something that's ionizing this. So, yeah, this is a very provocative result. Okay. Next item here is that we were fortunate to be able to release our first data release this week on Tuesday. And so this is releasing our year 1 images from and mosaics and catalogs and deep spectroscopy in the region of the Hubble ultra deep field. It's about 25 square arc minutes. And we do this because we think that this area is just a very important community field, and in particular, the cycle 3 proposal deadline is coming up, and we would really encourage people to dig into this data and think about what you could do for the October deadline. There's a really marvelous viewer at this location, and so I'm actually going to break out of the presentation and go to the viewer. So this is actually a tool that we developed in the team. Brent Robertson and Ryan Housen took the lead on this. We actually developed this so that we could look at the data. Like, it was not done as a public outreach thing. It was done as like, this is a very complicated data set, and you're wanting to look around and see things. Let me go actually over to this other one. So here's our grand design spiral. And so oops. Oh, okay, let's, where to go? There we are. Okay, there we are. Okay, so there's the viewer. Thanks. Oops, but now I've gone too far. There, okay. So with this viewer, and this is a public, we've now been able to mount this on a public server. So I want to encourage you to take a picture of the URL and do this yourself, because when I'm having a bad day, too many committee meetings or whatnot, I go and look at this at the data to try to cheer myself up. So you can just pan around to wherever you want. You can come over here and select all the various types of combinations of RGB images. You can select out all the various bands of data that have been collected. So it's really marvelous for that. If I go over to this one, if you go to the second thing, you can actually click on a button to get the overlays of all of the near-spec spectra of individual objects. So it's really cool to be able to look around at this thing. We also have every object, and you can click on it and it'll pop up the full SED thumbnails of the objects, and you can see the photometric redshift estimate. So I think just really want to encourage people, this tool for me has been just wonderful to actually engage with the data, to sort of see how these really complicated, this is whatever, in this case it's only 14 bands of imaging, but it's really hard to mentally visualize, and if you're just sort of having to stick blinking between things. So this is a great way of actually looking at the data. Okay. All right, so again, there's the URL for that, and you can also get to it from our survey website. Okay. All right, so I want to spend the last bit of the talk talking about pushing the redshift frontier. The first thing to say is JADES is only partially done. Even though this was a cycle 1 program, turned out that because of the overcrowding in the schedule, we only got about 40% of the program scheduled in year 1. So we actually have a lot more data coming, and in particular, the region of sky that's in that viewer, we're going to be doubling the exposure time on in the coming year. And there's the majority of the spectroscopy is still in front of us, so that's going to be fabulous. We'll now be able to do our targeting with near-cam imaging as we hoped. So where is the redshift frontier? We've shown that we got a spectrum of a redshift 13 galaxy, so I think that's the highest redshift one that we would claim is certain. But we see these other candidates. So here's a candidate at redshift 15. Doesn't look as good as the rest ones, but you get something in a drop. Could be that. Here's a candidate at redshift 16. Maybe. These are not as confident, but that's weaker in F200. Here's one that's a dropout at 2 microns. So this is coming along and then drops out entirely at 2 microns. So that's a redshift 18, perhaps. So that's where we have published these as candidates, but certainly, as you can tell by my voice, I don't think that these are as confident as the ones at the more familiar redshift 8, 10, or 12. And so we're not proclaiming them really strongly because we see other counterexamples in the data. I'll show you some of those next, that we think leave us with some doubts, wanting more proof. And the types of contaminants that come in here are, first of all, that when you're looking at really faint objects, you're trying to see this Lyman drop, but any other spectral break, and in particular the Balmer drop, could potentially fool you. So if you have a stellar population that has a lot of A stars, then you might generate a sufficient Balmer drop that maybe you could get yourself fooled. And then the other problem is that these rest optical lines, in particular oxygen 3 and the Balmer lines, are very strong. And so if you have a situation where those lines are so strong that they're inflating the bands that are redward of the Balmer jump, then the combination of those lines and the Balmer jump can make it look like a shelf dropping off into the near UV. So those are the problems. So we are worried that the rate of false positives may be increasing with redshift, and it's driven also by the fact that we are actually starting to run out of filters. Once you only have 2 or 3 filters in the red, then you don't have as much constraint on the consistency of the SED. So we are confident with the bulk of the candidates because we have spectra successfully of 42 of them, but when you get out to these higher redshifts, I would express some caution. So examples of trouble. So here's one that looks pretty reasonable, right? Boom, 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 nothing. Boom, 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 nothing. But if you're in the front row and you look at the center of that image, you can see a little bit of emission at FO90W. So in fact, we think this is a Balmer jump at redshift of order 5 that is kicking back up again in the far UV, and you have to have pretty deep data to see that. Here's another example that nobody would believe nobody would believe that this is a high redshift galaxy because you see plenty of stuff over here. But what I want to draw your attention to, and this is a little hard to see, is that there's a noticeable change in the morphology between here and here, right? On this, the right-hand side of this is only supported by the filters over here, and then it all seems to disappear there. So, okay, of course this is a low redshift galaxy or mid-redshift galaxy, but the point is there are portions of mid-redshift galaxies which can successfully look like a big drop at around 2 microns, and if it can do it next to its neighbor, maybe it could do it as the whole thing. And so this is another example of an SED that could be trouble. Again, this one's so bright that you would never be fooled by it because we detect it all the way down, but in fact, although this thing is super duper bright, the drop here is pretty strong, and if you had much lower signal to noise data, you might think that you could get fooled by something like this. So these are the examples that we are kind of concerned about. So we have a program that was approved in cycle 2 that we hope will help to address these problems, where we'll be returning to the deepest part of our year 1 field, but now doing it with medium bands, here, 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 and here. And the intention here is to A, be able to reject emission lines because we'll be able to detect things in the medium bands compared to the broad bands, and B, to be able to constrain the sharpness of the break more, to constrain where the on-off part of the break more tightly, so that we can actually argue that things really are Lyman drops, which are completely sharp, versus Balmer. So we'll be doing this in October, some October, hopefully 2023, but that's up to them. And then at the same time, this will produce a ultra-long spectroscopic exposure on the Hubble ultra deep field. So this is a twofer here. Alrighty, so to start to wrap up, JWST is revealing large populations of galaxies at high redshift. I think the main takeaway is that these populations are heterogeneous. We see complex morphologies. Here's a beautiful example of a clump at redshift 7 that shows, of order 10 clumps. They all disappear at FO90. They all show oxygen 3 emissions, so it really is at redshift 7. But we're seeing these complex morphologies, or perhaps some examples of compact groups. We see some examples of large-scale clustering. The spectra are not all the same. We see variations in line ratios, examples of very high specific star formation rates, examples of very low specific star formation rates. And we see variations in Lyman alpha emission that's starting to reveal the details of reionization. So I think this is all just getting started, where we're now in the position where we have large samples, and the telescope clearly has the capacity to do these studies. And I think that as we go on into cycle 2 and beyond, it's just going to be a real gold mine. So I want to thank the JADES team and give a shout out to all the Cambridge locals. There's a big JADES cohort here, and I want to thank everybody for hosting this week. And I'll close with this, that we've been waiting for 25 years for this telescope, and I think that it's just going to be a transformative opportunity in astronomy, not just for this type of science, but for many things. We've just been waiting. There have been many questions that for the past 20 years, in galaxy formation at least, the answer has just been, wait for JWST. We just can't make any progress until we have JWST, and now it's here. So I want to refer you again to our data release and encourage you to follow the exploits of the survey. Thanks very much.